Howdy, everybody. All right, today we are going to go back into talking about solving systems of linear equations. Remember, a system of linear equations is two or more linear equations that we talk about at the same time. And normally what's going to happen, we're going to have one equation, let's say, looks like that. The other equation looks like that. And what we're really concerned about is this point of intersection right here, because that is considered my solution to a system of linear equations. Anyway, what I have drawn right here is solving a system of linear equations by graphing. I graph both of them and physically find where they intersect. The second way of solving systems of linear equations that we talked about last time was called by substitution. And what that is, it's completely algebraic. We don't draw anything, and we just follow a series of steps. So in case you have forgotten or you need a little bit more practice on that, here are those steps. Step one, first thing we are going to do is we are going to solve one of the equations for x or y. Notice that or, it doesn't matter which variable we solve for or in which equation. All I need is one of these two equations has to be solved for a single variable. Well, if you look at this second one here, y equals negative 2x, it is already solved for y. So I am actually done with step one. Great. We have solved one of the equations for y. I go on to step two. Plug what that variable is equal to into the other equation. So let's think about what that means. I know that y equals negative 2x. So what I can do is where I see y on the other equation, instead of putting y, I can just put what it's equal to, which is negative 2x. When I do that, look what happens. I get 3x plus 2 times, what's y now? Y is negative 2x. And that equals 7. Step 3, solve for a variable. Notice what that means here is that there is only one variable left now at this point. It's only going to be x. If we had solved in step 1 for x instead of for y, then the only variable left would be y. But the point is, once we get to this step where we are right now, we only have one variable left. Once I have that one variable left, I just do simplification steps and solve for that variable. So let's go ahead and do that. So I get that 3x plus, well, 2 times negative 2 is negative 4, so it's plus negative 4x, or as everyone knows, this right here, plus a negative, is just the same thing as minus. So I'm going to say 3x minus 4x equals 7. Well, 3x take away 4x is negative 1x, or just negative x. I know that negative x equals 7, and so that clearly means that x equals negative 7. If you weren't sure about that, just multiply both sides by negative 1, or divide both sides by negative 1. Nevertheless, I get that x equals negative 7. So look at step 3 over here. Step 3 is done. I have solved for a variable. I have solved for x. But I'm not done. There is a final step. Plug that solution into either equation to find the other variable. Okay? So let me clear a little bit of this just to make it a little less confusing here. I don't need that. Now, what I'm going to do, I am going to take this x. I know that x is negative 7. And I'm going to either plug it in here into this second equation, or I'm going to plug it in here into this first equation and then solve for y. Now, which one do I use? Well, I'm looking for the one that looks the easiest to plug in and solve. And that's clearly the second one because there's a lot less steps there. It's just really one step. So I'm going to use that one. And notice what I do. Y equals negative 2x. But x is negative 7, so y equals negative 2 times negative 7. And I get that y equals positive 14. Now, the temptation here is to box your answer and call yourself done, but I'm not actually done because a system of linear equations has a solution that is a coordinate pair. So I write it like this: negative 7 comma 14 is my solution. And I know that if I did graph these two equations, the equation 3x plus 2y equals 7 and the equation y equals negative 2x, I know that these two lines would intersect right here at the point negative 7 comma 14. That's it. That's the reminder of what we're doing. Now we're going to do special cases today. Because remember, the three types of linear systems you could have look like this. One, you can have the normal one with two different lines. Two different lines. And what that'll look like is something like this. We'll have one right here. We'll have one right here. And it will have exactly one solution because it has one intersection. Okay? Now, the other kind we can have is two parallel lines. Okay, and what that looks like is we have one line like so, and we have another line like so. It doesn't appear that they have an intersection, which is because they don't. They never intersect because they are parallel and not the same line, so I write no solutions. Okay, and finally, we can have the same line. Same line. And so what that looks like is something like this. I start out with one line here. And then when I get my second line, it actually ends up that it's right on top of the first line. And so there are an infinite number of intersections. And so I write that there are infinitely many solutions. So my question today is, what does solving by substitution look like when I have no solutions or infinite solutions, infinite number of solutions? Okay, what does that look like? Well, that is the point of today's video. So, number one, solve the system by substitution. Notice, I have purposely made this look very easy so we know what this is going to look like before I start. These two equations have the same slope, but different y-intercepts. So they're not the same line, but you know they have the same slope, which makes them parallel. I know that if I have parallel lines, I am not going to have any intersections, so this is going to be no solutions. I know that before I start. Now let's look at what happens when I use the substitution method. Okay, first of all, step one, solve one of them for a variable. Already done. Okay, I have both of them solved for y, so it doesn't really matter. Step two, plug what one of them is equal to into the other. Okay, so y is equal to 3x minus 7. So in the first equation, I will just replace y with 3x minus 7. So I get this equation. 3x minus 7 equals 3x plus 7. And that should make sense, right? Because what this is really saying is y equals this guy, but y also equals this guy. So if y equals y, then this guy must equal this guy. So I have 3x minus 7 equals 3x plus 7. Now I simplify. Minus 3x, because I want my x's on the same side. That cancels out. That cancels out too. What am I left with? Negative 7 equals positive 7. Now, let me ask you very carefully. For what values of x does negative 7 equal positive 7? The answer is that's a trick question. Negative 7 never equals positive 7. So what happens when we have parallel lines that never have an intersection is when we try to solve by substitution, we will wind up always with something like this, meaning something that cannot happen. So when you get a false statement, negative 7 equals 7, you write no solution. Some of you will remember that we saw this already before when we were solving fancy equations that had no solutions. This is exactly the same thing. When I get a false statement, I have to write no solution. Let's do another one. Solve the system by substitution. This one's not quite so easily transparent what the answer is going to be, but nevertheless, we follow our steps. Solve one of the equations for a variable. The second one already is solve for y, so I am done with step one. Step two, plug what y equals in for y in the other equation. So I'm going to actually write down my whole thing. Negative 6x plus 8y equals negative 4. And then I am going to duplicate that. Negative 6x plus 8. But instead of the y, I don't want that anymore. I want what y equals to. And y equals 3/4 times x. Okay, so 3/4 times x. Now I have to solve this guy. And here's where you're going to have to remember all of the things that we have done, how we simplify various fractions and various expressions. Okay, so first thing, 8 times 3/4. This is 8 over 1 times 3/4. And remember, when I'm multiplying fractions, I can just reduce. This 4 becomes a 1, the 8 becomes a 2. This is my magic pen, so let me just do it permanently. The 4 becomes a 1, the 8 becomes a 2. And I am ready to proceed. I get that negative 6x plus 2 times 3 is 6x equals negative 4. Well, negative 6x plus 6x, negative 6 plus 6 is 0x equals negative 4. But wait, 0 times anything, 0 times x, 0 times anything is 0, so I know that 0 equals negative 4. Oops, that's not right. 0 can't equal negative 4, which tells us immediately I'm done with my steps because I have no solution. These are numbers that are not equal to each other. Okay? No solution. Moving right along. Solve the system by substitution. Now, look what I have here. Once again, on purpose, I have put these to look very easy because what do you notice? 9x minus y equals 12. 9x minus y equals 12. It is the exact same line. Clearly, you know that when you have the exact same line, it will be one on top of the other, and so you're going to have infinite number of solutions. Nevertheless, let's see what happens when we try to solve this by substitution. First thing, step one, solve for one of the variables. This is not done for me yet, so I'll take the first one, say, and I will solve for y. 9x, actually, you know what? I'm going to solve for x because I haven't done that yet. I haven't shown you guys that you can do that yet. So I'm going to solve for x because it's exactly the same thing. So I'm going to add y to both sides because I want x by itself plus y. And I have 9x equals y plus 12. Great. Now I divide everything by 9 to get x by itself. X is equal to 1/9 y plus 12 over 3 can be reduced. 12 becomes, they both have a common factor of 3, so divide by 3, I get 4. Divide by 3, I get 3. So 1/9 y plus 4/3. Now, it's a little bit ugly. It probably would have been a little easier if we solved for y, but I wanted to show you guys that you can solve for x. Now look what we can do. We can take that. Well, first I can group everything together and shrink it down. I'm supposed to be able to. Okay. So I shrink that down so that I can come back up. And now what I'm going to do, I'm going to plug my solution for x in for x on the other side. So look what happens. I get that 9 times x minus y equals 12, which means 9 times what x equals, 1/9 y plus 4/3 minus y equals 12. Now, anybody thinking this looks super ugly? Two things. One, you're right. And two, it's all going to get pretty real quick thanks to the magic of fractions. So first I have to distribute this 9 to the 1/9 y, and then the 9 to the 4/3. But what that means is I have to multiply this 9 over 1 now by each of these other fractions. So 9 times 1/9, the 9s are going to cancel, and I am just left with 1. So I get y. Now I'm going to, let me actually undo that, because I need this to come back. So I'll use my magic pen. The 9 is going to reduce, and so I get that y, 9 times 1/9 y is just equal to 1y or y. Now when I do the 9 times 4/3, again, the 9 and the 3 will reduce. 9 becomes a 3, the 3 becomes a 1, and so it's just 3 times 4. And so I have y plus 3 times 4 is 12. So y plus 12 minus y equals 12. I'm going to combine my like terms. So I have them on the same side. I'm just going to rewrite this so they're next to each other. Y minus y plus 12 equals 12. You probably see it already. Y minus y is just 0. So I cross those out because they add up to 0, and I am just left with 12 equals 12. Once I get that a number equals itself, this is no longer no solution because this is true. So what I do, I just write all solutions. Or, sorry, not all solutions. What I mean to say is infinitely many solutions. So infinitely many solutions. Because this 12 equals 12, or a number equals itself, tells me that I have parallel lines. Let's do one more. Solve the system by substitution. Okay, so step 1, I have to get one of these solved for a variable. This first one looks like my culprit that I should start with. And the reason for that is I have this term y that doesn't have a coefficient in front of it other than 1. So that tells me that's probably where I should start. So I will start there, and I will solve for y. So 5x plus y equals 22. And then I'm going to solve for y, so minus 5x minus 5x. I have done it. I've solved for y now. Y equals negative 5x plus 22. Step 2, I now plug what y equals to into the other equation. So negative 15x minus 3 times y is negative 5x plus 22, equals negative 66. Now, it's clearly time to distribute. Negative 3 times negative 5x, negative 3 times 22. So I get negative 15x minus 3 times negative 5 is positive 15. So positive 15x. Negative 3 times positive 22 is negative 66. And that's going to equal negative 66. Well, I need to combine my like terms. Negative 15x plus 15x adds to 0. So I get that negative 66 equals negative 66. That's always going to be true. So I write infinitely many solutions. Okay, so let's recap this real quick. There are 3 things that can happen. 1, if you get x equals a number, y equals a number, then your solution is x comma y. I realize you don't have this slide right here, so go ahead and write it somewhere where you can find space. It's not going to take too much space here. The second thing that can happen, some number a equals a different number b, and a is not equal to b. These a and b are just holding the place of numbers. So an example of that would be 5 equals 7. Clearly, that's not true. And what happens there, instead of having x comma y as our solution, what we have is no solution. Okay? And then finally, what I can have on number 3 yeah, what I can have for number 3 is I can have A equals A, where A and A are the same number. So for example, 5 equals 5. And what I write there is that there are infinitely many solutions. And those are the only 3 things that can happen, okay? So why don't you go ahead and do the your turns, number 5 and 6, and I will see you in class tomorrow.